And now the last one from the application session I would like to introduce you is Dr. Tahir Rabbani, and he's founder and CTO of Viztronics Smart Solutions. He will talk about the 3D inspection and bin picking of orthopedic implants using deflektometrie. Mr. Rabbani, please come here. And the floor is yours.
Okay, should I start or?
You can just start, yes.
Okay. Hi everyone, good afternoon. I think as you introduced, my name is Tahir Rabbani and I'm R&D Director of Viztronics Smart Solutions. Today I would be talking about application of 3D deflectometry for bin picking of orthopedic implants. I think if I can, this to go to next slide, is it? Yeah. So just starting with basic introduction to the company. Viztronics is a startup based in Dublin in Ireland. Our focus is mainly to provide 3D solutions for inspection and quality control. And we cover quite a range of sectors in 3D imaging, from microscale imaging to big scale imaging for bin picking. And we also have technology in the space of deflectometry, which can be used for any kind of specular surfaces like polished metal or glass. And basically, we provide ready-made 3D solutions as well as customize our technology to kind of solve problems which are more challenging and can't be really solved using off-the-shelf components. So in terms of technology, our core technology is smart phase. It's structured light based engine using phase shift. And we can use it with triangulation. If you, oh, sorry. Is there a pointer? No? OK. So if you look at the bottom right, using smart phase with a small field of view, we have two sensors called micro-Z and micro-Z HD. Which can give you a field of view from 50 to 300 millimeter, and the resolution can go from 5 to 30 micron. Similarly, for big field of view for bin picking, we have a product, Z-Flex and Z-Flex HD, which can go from 300 to 2 meters, and you can use it for bin picking or inspection of big field of view. And today's presentation would be focused more on DeflectoZ, which uses deflectometry, again with smart phase for imaging any kind of reflective surfaces. As you can see, we can image ceramics, polished metal, transparent glass, or any kind of other surface which is specular. And today's presentation is mainly focused on using DeflectoZ for inspection and bin picking of orthopedic implants. So this is just giving some background about where orthopedic implants are actually used. So basically, they are mainly to replace bone structures in knees or other parts of the body. With age, as those parts deteriorate, you have to replace them with metallic components, which are called implants. They are typically manufactured from titanium or chromium and have very polished finish, almost looking like mirror. And that makes it very hard to image them using standard 3D imaging technologies, whether laser, structured light, or stereo, right? And I'll go to the next slide. So if you look at the top the top right image, you can see the metal blank where the implant starts from, and then it goes through different processing and polishing stages, and it ends up being a kind of mirror-like finish, right? And what we want to do is design a system that can detect the part, position it, right, find its pose, and is able to pick the part using robotics, mainly for automating the processing of loading and unloading of these parts into different processing machines. Another reason this kind of implant bin picking is important is because the whole process of manufacturing is moving to 3D printing. And as you 3D print these parts, it's very important to inspect the dimensions and also automate the processing and manufacturing process. So I'll start with the unpolished implants, which you see in the bottom half of the screen. They have a diffuse metallic finish and can be easily imaged using any standard 3D imaging technique. So what we used basically was a structure light approach. If I show here, you can see the difference between the diffuse and the polished parts, right? The diffuse part has a very good structure where you can clearly see the stripes, and from the deformation we can calculate the 3D. But when you look at the specular and fully polished implant, it's actually reflecting the structure from the size of the bin rather than from the projector itself. And as a result, the point cloud that you get from the polished part has more noise rather than data. So this is the result for the unpolished part, which has a diffuse finish. And as you can see in the bottom image, we get good stripes there, and we can easily convert that into a 3D point cloud, which can be then used for bin picking. That's another example. But when we do the same technique on the polished implant, basically you're seeing the reflection from the sides rather than from the projector, and the point cloud that's produced is mainly noise. It's not really usable for bin picking by a robot. I think that's another example of the polished implant. So I think for this kind of polished finish, what we proposed to do was to use deflectometry. Just to give a high-level background of how deflectometry works, basically deflectometry exploits the reflective surface of whatever object you're trying to image, and basically uses either an LCD screen or some other display to generate structural light, which is then reflected from the object that you're trying to image. You can use 2 or more cameras to cover the object, and once the whole system is calibrated by looking at the reflection of the structured light, you can convert the results into a full point cloud. So that's the typical setup that you would have. Basically, you have an LCD pattern projector, which will go through a sequence of structured light patterns. The object that needs to be imaged is placed underneath. And as we go through the sequence, the cameras are looking at the reflection of the projected LCD pattern in the reflected object, right? And one reason we have to use phase shift or some kind of defocus-resistant analysis mechanism is because the camera is focused on the object, but the pattern is further away, right? So you can focus on the object, but not on the pattern. So the pattern would always be out of focus. And that means any kind of defocus-resistant structured light approach is the only one which is going to work. If you're using binary or some kind of focus-dependent structured light, that won't really give you the result and resolution that you require. So in terms of the whole deflectometry process, we have a few steps. Basically, you first do the camera calibration of your stereo setup, including the lens distortion, right? Then you have the geometry calibration. Similarly, you need to calibrate where the LCD is in the whole setup so that you can actually do the full ray tracing. And once all this calibration is complete, you go through the structured light sequence, decode it, and that gives you each pixel which is being reflected by the object. And then doing the ray tracing calculation, you can convert that back into a point cloud. So this is just showing some typical images. You see the LCD screen, the polished object with the 2 cameras which are looking at the object, and just one example image where you can see the reflected pattern in the orthopedic implant. So I'll just go through the typical sequence that we use in terms of structured light. OK. So you can see basically we have a progressively increasing set of frequencies, both in X and Y. And by analyzing that on the reflected object, we can figure out which pixel on LCD was reflected and seen by the camera. This is one of the example images, right? So you can see the left camera image on the top, showing the reflected pattern on the orthopedic implant. The right camera image at the bottom. In the middle, you see the results of the analysis of the structured light. So it's showing you the wrapped phase image, but after unwrapping and doing the ray tracing calculation, basically we get a full point cloud, which has enough coverage to be able to pick up the part. That's another example. Here again, you see the left and right camera image with the reflected pattern being seen on the orthopedic implant. The middle image shows you the results of the analysis of the structured pattern. And the last image is showing you the point cloud that comes out of that analysis. And here, basically, just an example of matching the point cloud to the CAD model. So the point cloud doesn't have like a full coverage of the orthopedic implant, but there are enough points there that once you match it to the CAD model, you know exactly what the pose of the object is, as well as the position of the implant in the bin. And that's enough information for the robot to be able to pick it up. So that's some images of the setup that we had. You can see the screen, the two cameras, the bin with the polished implants in it, and at the bottom you see the point cloud, and it's matching with the CAD model. So as a next step, basically we want to expand the solution to be able to do both the polished and unpolished implants using one sensor. So what that would require is that we would have an LCD screen with 2 or more cameras, but also a projector. So one sensor then would be able to basically image both the polished and unpolished implants, and then we can use it for bin picking. So I think that was the last slide I had. I don't know if there are any questions or.
Thank you, Mr. Rabbani.
Thank you.
And no, there are no questions.
OK, thank you.
OK, so thanks to all for attending the application session of the Industrial Vision Days. And thanks to the 3 speakers. And yeah, have a good day at the fair.